Welcome to the Heatwave podcast, conversations about the climate change with people who actually know something about it. I'm Wojciech Pecka, and today I will speak with Ela Gillbert, a climate scientist researching polar regions. Welcome, Ela.
Thanks for having me.
Ela is also a very capable science communicator, and you can follow her on YouTube and Twitter. Subscribe to her channel, Dr. Gills, with the Z at the end, and so you can get her great explainer videos. For the start, Ela, what actually you do in your climate research?
So most of my work is trying to understand the atmosphere, the weather, and the climate of the polar regions. So I'm mostly interested in Antarctica historically, but I mean, I also work in the Arctic as well. So what I do on a kind of day-to-day basis is try to use computer models to understand the processes that are going on in the polar regions, in the atmosphere, how that interacts with the ice of the polar regions, melting, precipitation, this kind of thing, and then looking further ahead into the future to figure out how that might change.
Yeah, so you focus both on Arctic and the Antarctic, right?
Yeah, I mean, most of my background has been in the Antarctic. So I work at the British Antarctic Survey,
Yeah.
which, despite its name, does also do Arctic research. But historically, I've mostly focused on Antarctica. But I'm, broadening my horizons and including both poles now.
Cool. And what did you bring to researching like polar regions or Antarctics especially? Do you
I guess
remember how did you like became interested in the topic?
Yeah, I think it was a bit of a gradual process, to be honest. First kind of discovered meteorology, so the study of the weather, in when I was at university doing my undergraduate degree,
Mm.
and it was kind of an accident that I sort of stumbled across meteorology in the first place.
Mhm.
And then later on, I've always been fascinated by the wilder parts of the planet and
Mm.
the kind of more remote and less known places. And I feel like Antarctica is particularly, it really epitomizes that spirit. It's very distant psychologically and
Yeah.
physically. So
Mm.
the draw to it was really trying to understand this extreme and fascinating and quite mysterious continent. And to combine that with, I mean, I've always loved understanding how things work and processes and mechanisms, and the weather and the atmosphere provides ample opportunities for trying to figure that out. And also in Antarctica or polar science in general, there's still quite a lot of stuff that is still to discover, still to learn.
Yeah.
Which is a bit different to the way things are elsewhere on the planet. So it feels like a really alluring subject material, and I've always been fascinated by it. And then as soon as I started studying Antarctica, that was it. I was really hooked, and I've never looked
Yeah.
back.
And have you been to the Antarctic?
Yeah, I've been very lucky. I've been to the
Mm.
Antarctic. I've also been to the Arctic a couple of times, and every time is always an absolute dream. It's an absolute joy. Going to Antarctica was, yeah, honestly, such a life-changing experience. It's, I guess, such a different environment
Hmm.
to the ones we're used to. It's not at all. I live in London, like it's
Yeah.
very urban. I often spend time in other kind of European cities, and it's not at all anything like that. And that in and of itself is an amazing experience. I think being in a place which is purely devoted to scientific discovery and international
Mm.
collaboration is a really inspiring environment to find yourself in. Not to mention, of course, the actual environment, which is incredibly inspiring as well, because it's this uh, awesome, in the truest sense of the word, wild place which
Mm.
has the extremes, is completely ice covered pretty much, and it's just such an otherworldly experience, I think.
Uh, and how does it work? Like, do you travel there by boat or plane, and then you are there on some like scientific station or something? I cannot really like imagine how the life is for humans is sustained there.
Yeah, it really varies. It depends what you're doing.
Mm,
So for me, I was stationed at Rothera, which is the British Antarctic Survey's station on the Antarctic Peninsula. And it's usually, I mean, you can get there via boat or via plane. The way I went was you fly to the southernmost tip of South America, basically as far south as you can go on a commercial airline.
mm,
And then Bass has a plane that flies you from there to the Antarctic Peninsula. Other colleagues would arrive by ship, especially the oceanographers who want to, they
mm,
prioritize the oceans.
yeah.
So that's where they do their science. For me, when I was there, I was doing airborne measurement campaign. So
Hmm.
we were using small aircraft to measure the atmosphere essentially to gather data to help
Yeah.
understand
So do you measure like temperatures, humidity, or something? Uh,
a variety of different things. Yeah. So temperature,
mhm.
humidity, winds, the kind of the flow of different quantities like carbon dioxide or methane from
Uh-huh.
the top of the ocean into the bottom of the atmosphere, energy, all sorts of different things. Basically, once you're flying little aircraft, it's expensive and difficult. So you want to catch as much stuff as possible. So you measure
Okay.
pretty much everything that you can, which is a really useful way of gathering data. And yeah, we were living on the base most of the time, and there are many, many bases around Antarctica, all operated by different countries. But yeah, it's kind of, I guess, the closest thing
Mm.
to the space station or something.
Yeah,
They
I see.
have these little communities that are cut off for some of the year, and then in Antarctica in the summer, lots of scientists come in, they do some research, and then they go away again.
Yeah, so have you been there in summer or how
Yeah.
long have you been there?
When I went, I think I was there 6 weeks
Okay.
in the summer. Yeah. Peak summer,
Yeah,
24-hour daylight.
yeah, yeah, that was daylight all the time.
Yes.
Yeah, and how
Honestly,
how was it like mentally or
well, I think it's better than 24-hour darkness.
mm,
But yeah, you need good blackout blinds. It does. I've definitely found on the way home that because obviously it was midwinter when I was going
yeah.
back to the Northern Hemisphere, I found that I really missed the darkness, and I hadn't realized until I
Yeah.
got back into the dark. I was like, oh wow, this is this is something I haven't had in my life for a little bit. But yeah, no, it's a quite a wild thing to experience, but you do get used to it.
Yeah. And what temperatures are there in summer?
I think when I was there, it wasn't that cold or that warm. Like it was -10 and then it got up to plus
Okay.
5 one day.
Hmm.
But it's not actually that cold in the summer on the peninsula. It's not quite like the stations high up on the Antarctic plateau, which get down to like, -60, 70,
Yeah.
80
Yeah.
sometimes.
That's crazy.
Yeah.
Well, yeah, okay. And maybe can you talk a bit more about like some basic characteristics of the Antarctic as continent? Because as you said, it's like for us, especially in the Central Europe, it's like, kind of terra incognita. And what is it?
Yes, I think when we compare the Arctic and the Antarctic, for example, one is
Mhm.
a frozen ocean surrounded by continents, that's the Arctic, and then Antarctica is literally the polar opposite. So it's a frozen continent surrounded by ocean. It's enormous. It's like the size of, I think, Mexico and the US combined. It's massive,
Mhm.
and it's right at the bottom over the South Pole. It's 99% covered with ice. It's very rocky underneath, and it's very steep terrain. It's very high
Yeah.
up, so it's like super cold.
Mm.
And because it's its own continent that's completely isolated, it means that you have quite a unique setup where it's completely surrounded by ocean, and you have
Mm.
these wild winds that kind of circle the continent. If you've ever come across the phrase the Roaring Forties, that's part of it
Yeah.
because these winds are at 40
Mm.
degrees south and they're super fast and they're really
Yeah.
famously difficult to travel across on boats. So
Mm.
sailors always used to dislike going that far
Yeah.
south. And similarly, you have the same sort of pattern in the ocean because they mirror each other. And you have this current that circles the Antarctic as well, called the Antarctic Circumpolar Current, very aptly named. And this is as well one of those things that kind of cuts off the
Mm.
Antarctic. So the atmosphere and the ocean both kind of encapsulate it in its own little Antarctic bubble, which makes the climate quite unique,
Mm.
and makes it really cool to study.
Yeah, and how much ice is there?
A huge amount. So there's enough ice that if it melted, the oceans worldwide would be raised by 58 meters. So it's a lot. Like in some places, the ice sheet is 4 kilometers thick. It is really a lot of ice down there. And I think on average, it's about 2 kilometers thick.
Oh,
So it's a lot of ice.
yeah, yeah. That's I know how and how the ice behave. Like I noticed that I always imagine that that the ice is basically stable, and I was pretty surprised and realized that like in longer perspectives it's basically kind of flowing or something. That's like kind of living thing, not like in origin organic way of living, but it's like definitely moving. So can you kind of explain the processes which drives this movement, and if there are like, for example, some different type of ice which could be important for us to understand?
Yeah, so just like a river, glaciers and ice in Antarctica flows. It's just a lot slower. So it's just like a frozen river, if you like, a big lump of water that's
Yeah.
gradually moving. I think, yeah, it's going if and standing on a glacier, if you've ever had that experience, you are quite struck by actually how dynamic it is. In my experience, I've stood on glaciers in Svalbard, for
Mm.
example, and they just make huge amounts of noise because the ice is
Yeah.
constantly shifting, it's constantly cracking and popping and
Okay.
making all this noise. And in the same way in Antarctica, if you are in a boat not too close, but close enough
Mm.
to a glacier front, you see stuff falling off all the time. They make funny
Mm.
noises. They kind of groan and creak and make all of these wild, kind of guttural animal noises. And that's literally because the ice is moving and it's all under this like stress as it goes downhill.
Mm.
So in Antarctica, we have the ice sheet, which is kind of what you might consider an ice cap, like a lump of ice on rock underneath, so on land.
Mhm.
And because it's so high up and the terrain sort of slopes downwards, that ice begins to flow in these
Mhm.
ice streams, or frozen rivers, and that's like what you would call a glacier. So the flowing part flows down the terrain, down the mountains, and reaches the sea at some point. When it reaches the sea, it sort of spreads out on top of the ocean because ice floats, as you know from having
Yeah.
ice cubes in your drink, and it turns into this big platform. So you have these platforms of
Mm.
ice around the edges of Antarctica called ice shelves. And
Mm.
you also get them in Greenland, but not quite to the same extent. So these ice shelves are floating ice, which means that they kind of just sit on the top, but they act as a sort of cork in a bottle, if you like. So they
Mm.
hold back the glaciers from
Yeah.
flowing from the ice sheet down into the ocean. And it means that the ice flows more slowly into the sea and it doesn't kind of break away so often. Then we've got icebergs, of course, which break away from the edges of ice
Mhm.
shelves. The ice sheet is constantly being replenished by snow. So every time snow falls on the ice sheet, it adds extra ice eventually, like it gets compacted down into this dense ice. And that means that when it's kind of in balance or a healthy ice sheet, it means that what goes in from snowfall is balanced by what breaks off around the edges from icebergs, for
Mhm.
example. Um, and that is in an ideal world, obviously. Then we've got the final kind of ice, which is sea ice, which also floats. And this is much more transitional ice, basically. So it doesn't last for anywhere near as long. Every year between summer and winter, the amount of sea ice that surrounds the ocean increases in area by 6 times. So
Mm.
it's increases sixfold between summer and winter. So lots of it is like only lasts for 1 year, for example, and that would get like moved around the continent by winds and ocean currents and things like this. And the sea ice is also behaving quite strangely at the moment. And all of these are very important components of the polar system and the Antarctic climate system, and they have impacts on ocean currents, on weather patterns, on ecosystems, and all sorts of other stuff.
Yeah. And can you say like what was what is the development in past like decades in Antarctic, or is it like, and maybe to compare it with the Arctic, like because we can see like pretty like big melting in the Antarctic. Can we see the same in the Antarctic, or is it behaving differently somehow?
Yes, I think the Arctic in some ways is easier to understand because it's quite a simple picture. And that's mainly that we've got Greenland, which is an ice sheet, and that's melting a lot from warming temperatures. And then we've also got the other half of the Arctic, which is not half, the other part of the Arctic, which is the sea ice, which has been declining really fast for quite a long time. So it's declining by 12 or 13% per decade, and that story is quite clear and easily understandable. The Arctic has warmed 4 times as fast as the rest of the planet. All of this stuff is quite easy to get your head around. In the Antarctic, it's a little bit more complicated as a picture because, first of all, it's so big and there's so many different kind of elements going on. Historically, Antarctica was thought to be a little bit more stable than the Arctic, was warming less quickly. In more recent decades, there's been a lot more warming on parts of the Antarctic Peninsula. So for a little while, the Antarctic Peninsula was the most rapidly warming region on Earth. But the East Antarctic, which is huge and absolutely enormous, was not really changing very much. More recently, the West Antarctic has been losing ice really, really fast. And you may have heard of glaciers like the Pine Island Glacier or the Thwaites Glacier, which has been perhaps unhelpfully termed the Doomsday Glacier by lots of media outlets. But all of these glaciers are losing ice really, really fast in the Antarctic at the moment, and it's contributing a huge amount to sea level rise. I mean, Thwaites alone contributes 4% of global sea level rise, and that's just one glacier. That's just it's quite mind-boggling actually that how much ice it's losing. So the Antarctic is quite an interesting one because different regions are behaving differently and have done behaved in different ways at different moments in time. And then the sea ice picture has been also really hard for scientists to understand because for many, many years, sea ice in Antarctica was increasing, which is not what you would expect from a warming climate until around 2015 when it started plummeting. And then ever since we've had pretty record low levels of sea ice, including last year, which was just absolutely off the wall in terms of the amount of sea ice. And this year is actually tracking along with a kind of similar trajectory. So it's quite, there's a lot going on and there's still a lot to understand scientifically. But Antarctica is changing and there's no doubt about that.
Yeah, and is there some like explanation for the fact that the sea ice around the Antarctic was like growing for some time, or
yes,
still like yeah,
yeah. So it's again, I think it's a combination of multiple different things. So some of it is to do with ocean currents, some of it is to do with the behavior of those winds that we were talking about earlier. Some of it is to do with weather patterns and kind of airflow in the atmosphere, and all of this combining into specific modes that mean the sea ice was kind of gently increasing or kind of staying roughly the same. And then more recently, we think it's probably this drop is probably caused in part, at least, by ocean heating and the amount of heat that's persisting in the ocean, which is literally just because we've been pumping more and more and more heat into the ocean over the last decades. And also then combined with particular weather patterns and atmospheric conditions that sort of conspired together to make it a particularly extreme few years. And it's unclear how things will develop specifically, but it seems very likely that sea ice will continue to decline in Antarctica because, you know, it's consistent with the heating of the atmosphere and the oceans.
Okay, and then you said that there are some like differences between East and Western Antarctic, right? Can you go more into the details? What's the difference there?
Yeah, so in Antarctica, we have like three main regions, I would say. So it's kind of roughly circular with a little bit that points out. So the bit that points out is the peninsula. It's in the name. But then we also have two main ice sheets. So one is the East Antarctic ice sheet, and this one is much bigger. And then we've got the West Antarctic ice sheet, and they're divided by a line of mountains that goes kind of through the middle. The West Antarctic is mostly below sea level, like underneath. So the bedrock is, it kind of drops downwards. Whereas the East Antarctic is on top of like basically mountainous plateau. So it's really a lot higher. It's a lot colder. That means it's a lot more stable. And equally, as you get kind of melting from around the edges, driven by ocean warming or atmospheric warming or whatever, if those glaciers and ice shelves start to retreat in the East Antarctic, there's not so many feedback processes that cause that to kind of continue indefinitely. On the flip side, the West Antarctic is the opposite side, kind of story. So because the seabed slopes backwards and it's below sea level, it means that any warm ocean water that gets underneath the ice can start to eat away underneath from below. And then as it starts to kind of eat away from below, it exposes a larger area because it's kind of pushing back. And because it slopes backwards, you get a bigger cavity underneath the ice. So more warm ocean water can get in, so more melting can occur. So this can kind of accelerate. And this is what we're starting to see. That's a sort of positive feedback, so a reinforcing feedback that we're starting to see, but is already hypothesized as well. And that's why we're seeing so much ice being lost from the West Antarctic at the moment. It's because there's all of these processes that kick in to kind of, once it's initiated, keep it going. And that's starting to be seen.
Yeah, okay. And and you can you see like that it's like going to melt from behind, or this is kind of, you know, invisible process in a way, or can you like measure it somehow? Or because I can understand that you can see like melting from the top from the plane or satellite or something, but how you can find those holes under?
Yeah, very good question. So I've got colleagues who work on this, and particularly in specific glaciers like the Thwaites Glacier, which is a very sensitive glacier. And there are multiple different ways that they look at this. So, for example, they use autonomous vehicles, so like submersibles, to go underneath the ice shelf to measure things like temperature and salinity and all of these kind of ocean properties that matter for melting. They can also drill boreholes through the ice shelves themselves, and that helps them measure all sorts of different stuff. Again, the same sort of things, temperature, salinity, that kind of thing, underneath the ice shelf, which tells you about how much melting is going on underneath, and therefore how much warm water is kind of getting underneath. There are also other ways. So you can use satellites to measure the change in the thickness or the height of the glacier, and from that you can infer the amount of melting that's happened. You can do other things with radar. There are lots of very clever ways that scientists can kind of infer these sorts of quantities or directly measure them. And the rise of things like autonomous vehicles is like really helping, I think, because this technology is really supporting this kind of novel data collection, which is really useful because it's a very rapidly changing environment and something that we really need to be monitoring.
Yeah, and when you talked about the Thwaites glaciers and that some media like calls it Doomsday Glacier, uh, like why is that, or is that something special
Yeah,
about it?
so the West Antarctic ice sheet in general is quite a unique
Hmm.
environment for the reasons that I was talking about with the sloping
Yeah.
bedrock underneath. Um, and Thwaites is thought to be a kind of keystone. So if Thwaites is lost, or if it completely retreats and all of the ice in Thwaites ends up in the ocean, then the theory goes that it would kind of drag in its surrounding glaciers. And there's lots of this is why it's thought to be a tipping point, because once the West Antarctic is gone, for all intents and purposes on human timescales, it would be irreversible because you'd
Mm.
have to cool the climate so much for that ice sheet to reform that it's basically a done deal. Um, but Thwaites is thought to be important because it acts as this sort of this keystone, essentially.
Mhm.
And once that irreversible decline is initiated, it's thought that certain processes, particularly they're very helpfully named Missy and Mickey, so
Missy and Mickey?
marine ice sheet instability and marine ice cliff
Mm.
instability. These are processes, some of which have been observed, some of which have not, that are that scientists think will probably allow this sort of runaway retreat because of the way. So marine ice sheet instability is more about that warm ocean water getting underneath and allowing the
Mhm.
ice shelves and glaciers to retreat really rapidly. Marine ice cliff instability is a bit more about these, as you lose ice, you get taller and taller edges exposed. And
Mhm.
those edges, when they're really tall, are very unstable, which means that they collapse in more quickly. And then that exposes an even taller cliff, and then that collapses, and then even taller. So
Yeah.
it kind of amplifies the rate of ice loss. We've never seen that happen before because we've never seen these conditions happen before, and they're very difficult to predict numerically with
Yeah.
computer models. So yeah, there's still lots that thankfully we haven't seen yet. But yeah, Thwaites is thought to be a really important part of this puzzle, and that's why there's a lot of research and attention going into Thwaites at the moment and the West
Mhm.
Antarctic in general. It's a real hotspot of both climate change and research.
Yeah, and when you said that this is like difficult to compute numerically, so there exists also the like modeling of the ice behaving, or is it like kind of separate from weather or climate models, or is it somehow linked together? How does this
Yeah,
work?
yeah, yeah. So we can do both actually. We can
Yeah.
most modeling of ice sheets is done as just kind of modeling the ice sheet itself. So these models predict things like the flow of ice, how much melting occurs, how much carving of icebergs, how much breaking away of icebergs happens, how the ice behaves under certain temperature conditions, things like this. And that would include a lot more complex processes, like, for example, this marine ice shelf instability stuff. Um,
Hmm.
but you can also model just the atmosphere, you can also model just the ocean, you can also model just ecosystems, for example, and you can also do them all at once. So these are coupled models, we call them, which basically bolt together our numerical model of the ice sheet with the atmosphere, for example, and maybe the ocean. And then it would help you understand the interactions between those different components. But that's also quite challenging to do. And it means that you have to have quite coarse resolution, which basically means if you're dividing Antarctica into a kind of grid, the individual boxes are going to be quite big, which means you can get a good understanding of how processes are going on, but you don't have a very good knowledge of the regional differences. So for example, Thwaites Glacier might be one grid box, which isn't very helpful if you're trying to understand the behavior of Thwaites Glacier. So if you want to zoom in on a specific region, generally that means that you have to use like a more sophisticated but single component model. So like an ice sheet model, for example.
Yeah. And you are working on weather model, right? Or climate model. Or
Yeah, so I use regional climate models, which are
yeah.
basically weather models. So the specific one I run is the same model that the UK Met Office runs to predict the UK's weather. So it's our operational forecasting model, but you can also use it for research purposes. And I use it in Antarctica and the Arctic. Not quite in the same way because we're like forecasting the past, if you like, a lot of the time,
Hmm.
as well as going into the future. But this sort of method is really helpful because you can gain a lot of understanding about the specific atmospheric processes, the kind of specific weather patterns, specific weather phenomena, how that interacts with ice and things like this. And of course, if you simulate periods that have already happened, you can cross-check it with the observed changes or the observed weather, which gives you confidence that the model is doing the right thing. And then you can use it to look into the future, which of course we can't observe.
Yeah. And did you try? I guess you tried to look in the future as probably is the like most like important thing for us. What did you see then?
Yeah, so I mean, the project that I'm currently working on is doing exactly that, and I'll have to get back to you on the results because it's still a work in progress. I think generally what we know from coarser resolution models, so
Hmm.
we have global scale modeling, which again tells you something about hundreds of years into the future, but it's not very fine scale. So there's not very much regional detail. So we know that, for example, Antarctica is going to be snowier, but also a lot warmer. So you're going to see lots more melting. The ocean is going to continue to melt away the West Antarctic, for example. And different regions will probably experience that in different ways. So in terms of the health of the ice sheet, that is determined by the balance between snow and basically what gets melted or what breaks away. And in the West Antarctic, it's going to be a lot more snowy for a lot longer,
Yeah.
basically, which is interesting because it means that melting at the surface isn't going to be very important. That is not the case for melting from the ocean, because melting from the ocean is already very important in West Antarctica. On the peninsula, because it's got so many mountains, you have lots more snow falling. And on one side, it's going to get snowier, the other side is going to get warmer. And then East Antarctica, somewhere in between. So it's, again, this like regional differences that are going to pop up. And I'm sure there will be lots of surprises in there for us too.
Yeah. And what would be like consequences for, I don't know, from the air system or for the, is it like some expected consequences for, I know, ocean circulation or weather patterns or climate patterns around?
Yeah, so I guess Antarctica is chief planetary refrigerator because it's so
Mm.
big, it's so bright, it's so white, and it's very reflective, this surface. It kind of acts like a mirror bouncing back the sun's energy back to space.
Mhm.
And this helps to keep the climate of Antarctica, but also the whole planet relatively cool. And that's a really important service that it does for us, and it keeps our climate the way that it always has been. And that means that if we start to lose sea ice, particularly in Antarctica, because there's so much of it in the winter, then that reflectiveness is going to change, and that has consequences for the global climate. Antarctica is also very important for establishing our weather patterns. So especially for countries in the southern hemisphere, the loss or the change in Antarctica and Antarctica's climate will have consequences for things like rainfall and temperatures and things like this, and generally just kind of weather phenomena that impact the Southern Hemisphere, Australia and South America particularly. But also worldwide, the atmosphere is a very connected thing. So actually, what happens in Antarctica will matter for all of us, even if we live in the Northern Hemisphere.
Mhm.
Um, and of course, if we start to lose ice, this will add to global sea levels, and that affects all of us. I think about half the world's population lives relatively close to a coastline. So this is something, and even if you don't live near a coastline, people who do live near coastlines might want to start moving where you live. So
Yeah.
all of this is going to have very profound consequences. Sea level rise is a kind of longer term impact, of course. So we have a bit more time to adapt to those changes that we see coming down the line.
Mm.
Whereas the impacts on weather patterns, for instance, are much more instantaneous. And then also we've got ocean effects. So the changes in sea ice, the changes in kind of ice shelves and glaciers melting, that all impacts how fresh or how salty the ocean is, and that impacts how the ocean currents are set up. So we have cold, dense, salty water in
Yeah.
Antarctica because of the climate and the way that the ice forms, which sinks, and then that establishes ocean currents, which circulate all sorts of things, nutrients, heat,
Mm.
energy all over the planet. So Antarctica's changing will have consequences for the atmosphere, for the oceans, for global sea levels, for human beings, and of course for the
Mm.
ecosystems that depend on it.
Yeah. And I heard like different speculations about the potential sea level rise, and that's actually this like disintegration of the West Antarctic is pretty uncertain territory, or so, and that our estimates are now, or IPCC estimates are now like maximum, it's like maximum 1 meter by 2100, or I, is it like this number?
Yeah,
Or
the IPCC is between 1 and 2 meters by
yeah,
2100. Yeah, but I think
and
lots
then
of people might consider that slightly conservative.
yeah, and that's like depends on how this disintegration will happen, if it will happen or something. There is some potential for surprises, right? Or
Yeah, certainly. Our actions today will make an impact on sea level rise by 2100 and beyond. So I think
yeah.
for the lowest emissions trajectory, which is basically a scenario where we pull out all the stops and we really, really go for climate mitigation. We really reduce emissions. We keep warming to 1.5 degrees or below. Then in that scenario, we see around half a meter of sea level rise by 2100.
Yeah.
On our current trajectory, so what our current legislated policies
Hmm.
will bring, it's between, I think it's probably like 0.75 and 1 meters of sea level rise in those specific estimates.
Yeah.
But lots of more recent research has shown that those estimates are probably quite conservative and sea level rise could be quite a lot higher. And that's not even before we start thinking about tipping points. And the tipping points, for example, the West Antarctic ice sheet or the Greenland ice sheet could lead to much, much higher levels of sea level rise. This is what people call a high impact, low probability
Hmm.
or low likelihood event. But in theory, there's a very scary graph in the IPCC report that came out in 2021-22 that has a dashed line above all of the sea level rise projections. And that dashed line goes up to, I think, 9 meters by
Hmm.
Can't remember the exact day. I think it's 2100.
Hmm.
And that is all about these high impact, low likelihood events, these tipping points, basically. And it
Hmm.
over time, by 2300, it goes up to maybe 15 meters, which is a completely mind-boggling quantity of sea
Yeah.
level rise, and of such a short amount of time comparatively. But yeah, these
Yeah.
projections are really uncertain because we don't know how the ice sheet will behave. If things happen kind of gradually, then we might avoid these kinds of tipping points, which would be great because it would mean that we have much more time to plan and
Hmm.
adapt. But if these uncertain events do happen, then it might be a very different picture.
Yeah. And are there some like clues from like history or from paleoclimatology or something how Antarctic behave in the history?
Yeah, so I'm not a paleoclimatologist, but I
Yeah.
can try and summarize as best as I can.
Hmm.
So there's evidence from rock cores, sediment cores, ice cores of these specific moments in time where you can infer that there was a big kind of injection of ice, which
Yeah.
people assume comes from these tipping points, these kind of collapse-like behaviors.
Hmm.
So that's part of the evidence that suggests that these do occur, as well as the kind of theoretical scientific understanding of how those processes might happen. Then there's also, you can run, just like you can run models for the future, you can run them for the deep past. So
Yeah.
you can simulate hundreds of thousands or millions of years ago and see how things would progress then when you had like a slightly different ice sheet, you had different continents, all this kind of stuff. And that's also where we get lots of this understanding from.
Hmm.
Obviously, we don't have the sort of direct observations of that
Yeah.
long ago that we do today. We can't have satellites or in situ kind of direct on the ground measurements of melting or things like this over many, many years. But from the data that is available, from those kind of proxies that you can use, the picture has been pieced together that these sorts of processes can happen fairly quickly. But of course, it remains to be seen because they're so
Hmm.
uncertain because there's not very many occasions to use. The sample
Hmm.
size is not very large,
Yeah.
thankfully. So it's still something that will remain to be seen.
Yeah. And yeah, then you touch some like problem with remote continent as Antarctic, and it is like the lack of data and lack of knowledge in some respects. So, like, can you try to summarize what is like the solid, knowledge in what climate scientists or polar scientists know about the behaving of of Antarctica and what where they move slightly more to the speculation and
I think the big picture we know very
mm,
well. It's like the big picture of climate change we know very well. More greenhouse gases leads to more warming. That's the
yeah.
simplest part of it. And
Mm,
Antarctica is no different. Antarctica is already changing quite a lot. We've seen warming in the atmosphere, we've seen warming in the ocean. We've been seeing that for many years. We've got lots of data to suggest that. And that's having impacts on the behavior of the ice. We're seeing that in the melt levels and the changing coastline, basically. That's having significant impacts on the oceans, on the sea ice, which we can see in satellite observations and direct measurements. We're also seeing more extreme events, so either things like extreme snowfall events
yeah.
or heat waves. Um, these kinds of extremes are happening more frequently because as you warm the climate kind of shifts, the natural envelope shifts, and we get more hotter conditions and we get snowier conditions because a warmer atmosphere holds on to more moisture, which means that you can dump more snow in shorter
Mhm.
periods of time. So we know that that is happening. We know that sea ice is changing, the ocean is changing, that the ice sheet and ice shelves are changing. Um, I think the uncertainties remain if we're talking about very specific regions. That's the sort of thing that we try to look at with regional climate modeling, because you can zoom in on a specific part of the Antarctic and try to understand what's going on now, what happened in the past, and what might happen in the future. And the other big uncertainty is, of course, with these sort of tipping points. We don't really, I think this is true of most tipping points, but there's a lot of uncertainty, a lot of question marks about where exactly the threshold lies. So if the West Antarctic or Greenland ice sheet is going to tip, or the Atlantic meridional overturning circulation, for example, what temperature of global average warming do we have to get to before that happens? And for lots of these systems, which are very complicated, very difficult to observe in some cases, we don't know that for sure. And indeed, it could vary depending on the climate. It could be a range of temperatures. In some senses, it's not that we don't know, but there's still uncertainty about how long you have to spend above that tipping threshold before the system is irreversibly changed. All of these things are active subjects of research that scientists are working on, scientists that work on tipping points. It's a real important study area, and definitely one that's attracting a lot more attention.
Yeah. And when you said you are working on like regional climate modeling, can you just like bring us more to your like typical routine at work, or just going to work and run some million years of simulation, or you are taking some data for the climate models, or how does it work? Because it seems like I hear all the time about the modeling, but very often I cannot really understand what the work is being done.
Yeah. So I guess at their heart, models are literally just math. So it's like a glorified calculator, if you like, which means that you have to start with something. And what we start with is data that we then feed into the model, or we kind of say, this is what's happening at the beginning, and then it will do all of those calculations, those mathematical equations, basically, to calculate what, given that starting point, what you get out after an hour or 2 hours or 3 hours or 5 years. So it kind of steps forwards in time, performing all of these calculations time and time again, to go forward through time. So the model, the kind of model that I run is the same one as we use for weather forecasting. So you give it information which is measured from all over the world. So, people releasing weather balloons or satellites observing the surface, things like that, weather stations around the world. So you have a good understanding of that starting picture. And then when the model calculates all of these, performs all these calculations, then it can step forwards into the future. And what you can do is you can kind of continue, if you're simulating the recent past, you can continue kind of giving it this picture of what current conditions is, as it goes along, to kind of keep it within the bounds of reality. When you're going into the future, of course, you don't have that luxury. So you have to, that's why weather forecasting is done over, like up to 10 days or something, because the accuracy reduces over time, because all these like micro uncertainties start to kind of amplify themselves, and it gets more and more uncertain as you go into the future. With longer term climate modeling, you're relying on your understanding of how things like carbon dioxide concentrations will change, which of course we don't know, but you can provide different possible scenarios. And that's the kind of thing that would introduce question marks about what we might see at the end of the century, for example, in really long-term simulations. But regional climate modeling generally tends to be high resolution, and then it will take information from a bigger scale model, which is driven by these different scenarios of human behavior. And then it kind of, I like to think of it as like a magnifying glass. So it sort of zooms in on specific regions, in this case,
Mm.
Antarctica, so you can get a much more detailed picture.
Yeah. So and then your work is just like actually doing the math, or just like you are part of the team of this like modeling group somehow, because it has to be pretty huge endeavor, no? It's
Oh yeah,
like or
definitely. So we run
and
them on
yeah.
supercomputers. They're absolutely
Oh.
enormous, and they're written in code, so you can adapt them to run for the periods that you like, or
Mm.
to examine a specific thing, for example. So what I would do is run the model. It has a little kind of software program that you can change some things
Mm.
and settings, and press go, tell it to the time that you want, that kind of thing. But if you want to then analyze the data, that also involves lots of kind of programming and coding to understand, because the data that it produces is like vast. So you've got so
Yeah.
many different things that you can look at,
Mm.
which means that, yeah, coding is a very big part of the job.
Mm.
Even just to kind of create the images and then the graphs that you can analyze
Mm.
requires quite a lot of code before you can get to that point. And then obviously the scientific part is doing the analysis of what it's being shown, and how things are changing and what it means.
Yeah. Okay, and when I move like more to the to the end of this interview, I would be interested in how like your work is like what is the impact on your personally, or is it like can be something sometimes like little bit depressive, or isn't it? It's like being witnessing like these huge changes and these risks of like possible quite low probability high impact scenarios. And how do you handle this? Do you think about that, or
Yeah, definitely. It can be super disheartening. It can be really depressing.
mm,
Um, yeah, it does affect my mental health, I have to say. But I think
yeah,
also that being part of the solution is
yeah,
the antidote to that despair, and also getting involved in like the communication of the science,
mm,
communicating the urgency of the challenge is really important. I guess, yeah, I'm aware that it's going to get a lot worse,
mm,
and that comes with its own kind of personal challenges.
mm,
But I also am aware that we still have a bit of agency in the matter. So I try to bear that in mind in my actions and my the way I choose to live my
yeah,
life, and the kind of things that I try to advocate for or push for. And also, you can't spend all your time thinking about it. You have to be, to some degree, a little bit desensitized, or be able to switch off from
yeah,
work. So yeah, I was a boxer for 12 years, so that
mm,
was my main outlet. I just
okay,
retired, so I'm going to need to find a new one now. But
mm,
yeah, lots of lots of
yeah,
ways of getting out of my head in that way.
yeah. And is it like common among your colleagues, or do you talk about like these issues, or is it like behind the professional, I don't know, uh, way of risk? How to get out of this sentence? You know, that's if you talk about possible futures or something on and mental health issues, or is it not the topic
I think
really?
increasingly more so, but still
Yeah.
not enough. I don't think people
Mm.
really appreciate, or at least acknowledge, the
Yeah.
impact that it can have.
Mm.
Um, it would be nice to have a bit more of that, I guess. But it does
Mm.
feel like people are talking about it a bit more, especially colleagues of my own kind of level, so who are maybe a bit earlier in their career. It
Mm.
does feel like it's something that's happening. But then again, also I think mental health generally is being talked about more now.
Yeah,
Which is
I
only a
see.
good thing. So it's not going anywhere. So we better start talking
Mm.
about it, or else.
Yeah, okay. And about your science communication like parallel career or something. I saw like several of your like videos, and what is the feedback for your work in this respect? Like,
Yeah, I mean, people like it, I think.
yeah,
I've won a few awards for my
mm,
communication, which is amazing. It feels great to have that recognized. For me, the communication is like one way I can use my strengths to really
hmm,
make a positive difference. And that feels like a very important form of activism, I suppose, for me, like
yeah,
a way to actually have an impact. And yeah, I think certainly the videos get used in educational settings like schools and
mm,
colleges and universities. I get lots of nice feedback from people. Also get lots of horrible feedback from climate
yeah,
deniers. I think that's part of the course. Um, and yeah, I think it's definitely I see my role as a kind of a translator because I'm lucky
hmm,
enough to have had the education and had the
hmm,
time to devote to research that I have, and also feel like I speak like a normal human being.
mm,
So there's this like being able to marry the two is really important, and not everyone has the taste or the skill for it. So being able to be that translator feels like an important thing for me to do. And I also really like doing it. It's like a very creative
yeah,
outlet for me.
mm,
Yeah, I like it. And the videos, yeah, it helps me kind of get stuff out. So I guess maybe that's also an answer to your question about how you deal with it. But
yeah,
creating that content helps me for sure, and I hope it helps others as well.
yeah. Great. So thank you for the interview. This
My
is
pleasure.
the this is the Heatwave podcast by Alarm Daily and supported by Heinrich Böll Stiftung. So don't forget to subscribe to our channel and also to channel of Ela Gillbert. It's found on YouTube and Twitter, right?
Yes.
As Dr. Gilbs,
Dr.
right?
Gales with a Z, yeah. Also on
Yeah.
TikTok and
Oh,
Instagram and all major platforms.
okay, great. So definitely check it out. Thank you for this nice interview and hopefully see you sometimes in the future. Bye.
Thanks.